In the first video, part 1, we talked a lot about what inverse functions are and how to prove that they are inverses of each other. In this video, we're going to focus on where things can go wrong. We had talked a little bit about earlier about difficulty with notation, and so yes, this can be confusing, but we want to know if there are more limitations to finding inverse functions. And if I look at this line here, this very mysterious line, as it's a clue that there is something out there that we have to be aware of. A function may or may not have an inverse function. So let's take a look at that a little bit more carefully. So here I have the function, a simple parabola y equals x squared, and we learned that if I were to flip this parabola over the y equals x line, if I were to draw the reflection of it, I would come up with this green line. This green function would be the inverse of our y equals x squared line. And you should take a moment, pause and take a moment and think about why there's something wrong here. Okay, so hopefully you should recognize that the green function is not a function. So even though we have a function y equals x squared and we flip it, we can create a graph that's flipped, that's true, but this is a relation, it's not a function. And so it actually doesn't work for us. And you might ask yourself, well, why doesn't it work? It should work. I can see it graphically. We've created this relation, so it's not a function. Why does this cause problems? And so I'd like you to take a look at this example. So if I take -2 and I put it into my function, y equals x squared, I get 4. Now if I put it into the square root function, the inverse, I get 2. I don't get the original. It doesn't work. And so we have to be careful, as it says here. We have to be careful that just because we flip it or algebraically we can come up with some sort of function that seems to work, they don't always work. So, but there are ways around this. So one of the things that we can do to fix this is we can restrict the domain. Restrict the domain. What does that mean? Well, yes, we've seen that there are issues with the y equals x line, our function here, but what if we were to only look at the portion of our graph that was positive from the domain, making the domain x is greater than or equal to 0. So in black here's our original function, and then red here would be the inverse function. That would be the square root of x, and those two would definitely work and would always work. And so for that particular case, then they are inverses of each other. So that's when x squared and the square root of x do in fact become inverse functions of each other if we restrict the domain to just x is greater than or equal to 0. So that's a trick that we can play to make one function an inverse of another function. Having said that, we still might not be able to find an inverse. But we'll go into that in a second. So how do we know what functions then do we need to restrict the domain, and what functions can we just know that it just always works? And there's something called the horizontal line test. So we've talked about the vertical line test, but the horizontal line test works in a similar way. So if I were to take an original function and I were to pass horizontal lines through that function, if I come across more than one point, then that function, if I find the inverse, that inverse will not work unless I restrict the domain. So the horizontal line test tells us if a function has an inverse. So let's take a look at a different function. Let's take a look at the cubic function. So if I were to pass horizontal lines all the way through this function, it only touches at one point. So that means that it passes the vertical line test, it's a function. It passes a horizontal line test, that means it has an inverse function. And so we don't have to play around with restricting the domain. The function that we get, y equals the cube root of x, is going to be an inverse function that always works. So that's how you know if a function has an inverse without playing around with the domain. Now, there is one other issue. So just because we can restrict the domain and create an inverse function doesn't mean that we're still always able to find an inverse function. So we'll take a look at an example here where we have a function and we are told algebraically if we go ahead and switch the x's and the y's and we try to solve. So if I try to solve for x here in this equation and get x by itself and then everything else on the other side, that we would have the inverse function. But as it turns out, we can't solve for x in this particular case. There's no way of undoing this, and so we're actually stuck. So algebraically we can't do it. We might be able to do it geometrically by flipping it over the y equals x line, but algebraically we don't have any way of doing that. So sometimes it doesn't work. All right, so that's it about inverse functions.